This is Lab 3, Black Hole Orbit. The objective explored in this lab is estimating the mass of the black hole, assuming that the net force is due solely to the net force on the system, which is only from the black hole. We're analyzing the rate of change in momentum and force while analyzing the parallel and perpendicular components of each to predict the path of the star. We found the mass of the black hole through using Newton's gravitational force equation. Newton's second law was also applied in this experiment. The ultimate mass was found to be 2.38 times 10 to the 11th kilograms. Curving motion was also analyzed by using VPython. The orbiting star was displayed by this model. The perpendicular force is represented by the blue arrow and the parallel force is represented by the black arrow. The parallel force indicated by the black arrow makes the momentum increase or decrease, which causes the direction of the star to reverse at a turning point, which is the closest location on the star's path to the black hole. The computational model successfully predicted the mass of the black hole through using Newton's gravitational force, which is the magnitude of the net force, which equals the gravitational constant, which is 6.7 times 10 to the negative 11th, times the mass of the star times the mass of the black hole, divided by the magnitude of the radius squared. The mass of the black hole, after rearranging the equation, was found to be 2.38 times 10 to the 31st kilograms. While using VPython, the initial conditions were entered. These include the mass of the star, which can be found here as 2.8741 times 10 to the 27th. Also, the time interval, which was 1 day, and it was converted to seconds, which ended up being 86,400 seconds, as well as the initial position of the black hole, which was used as the origin position, which is found right here. The star's motion was analyzed to obtain the approximate mass of the black hole. The gravitational constant was also added, which was found to be, which is actually given as 6.7 times 10 to the negative 11. This model fits well with the data if only the gravitational constant was acting on the objects in the system of only the star and the black hole. You can see that each component was altered to, first, the actual positions of the star data was read from a file that was previously downloaded, and it was imported into VPython to read. And from here, each of the delta x and delta y were altered to match to make sure they were reading the accurate data. And from here, the v initial and the v final were used to approximate the momentum, which also included using the star's mass, which was previously stated. The delta v and delta p were both found by accounting for the change in each of them, and from here the dp dt was found, which was also relatable to that of Fnet. From here, other information was found in order to ultimately find the mass of the black hole, which was used using the equation once again. That was the magnitude of Fnet times the magnitude of the star position minus the black hole position squared, which is also that of the radius squared, divided by the gravitational constant multiplied by the mass of the star. Ultimately, this mass of the black hole was printed, and the final value was found. In order to see an accurate model, I made sure to alter some of the scales within the programming, including the arrow scales of that of Fnet, F perpendicular, and Fnet parallel, so to make sure that you could accurately see each of the arrows. And it was also done in order to make sure that you could see that of the initial black hole, and I made the radius slightly bigger so that it could actually be visible relative to the arrows. Ultimately, if other objects were there, then the objects would exert forces on the star, which would alter how it would move around the black hole. So this experiment accounted for absolutely no outside forces. The Fnet, F perpendicular, and the F parallel components are all related to dp dt and dp dt perpendicular and dp dt parallel. The force and momentum are not equal, but the momentum change is caused by the net force. The momentum is observable and the net force is not. The what-if question asked if there was a different black hole in the same place and location of star, would it be possible to have the same mass for the same trajectory? The answer is no. With gravity being the only force, if the position of the star was the same for every point, there could be no other mass. Ultimately, for this experiment, the mass of the star was found to be 2.38 times 10 to the 11 using Newton's second law and the gravitational law.